Hello everyone, my name is Surish Rao Kumar Rao, matrix number 181091359 from RK23. So for this EET 208 project presentation, I would like to start our presentation now. So as an electrical engineer, every student was given an electrical system that consists of three-phase Y-connected generator, transmission loss, and a load with acceptance of power factor lagging uh, according to the ESA V version 3.0. So every branch of a balanced three-phase Y-connected transmission loss and the load powers a resistance and a reactance respectively. So every student was given randomly the line-to-line rated voltage of the generator. So three-phase voltage um, is a common method of alternating current, electric power generation, transmission, and distribution. The system is a type of polyphase system and is the most common method used by electrical grids worldwide to transfer power. So three-phase system is also used to power large motors and other heavy loads. In general, three-phase systems are preferred over single-phase systems for the transmission of power for many reasons. The frequency generated is determined by two wattmeter consists of two type of connection, which is Y and delta. So let the current flowing through the current coil of the wattmeter will be given as I1, and the potential difference across the pressure of potential coil of the wattmeter uh, will be V13, which is equals to the voltage 1 and voltage neutral minus to the voltage 3 and voltage neutral. So to obtain the value of voltage 2 and voltage 3, the phasor of voltage 2 and neutral is reversed and added to the phasor of voltage 3 neutral. So the objectives of this laboratory experiment includes the following, such as to investigate and analyze the three-phase Y-connected generator system, to evaluate the parameters of the electrical system in the context of transmission and load impedance, currents, voltages, acceptable voltage drop based on BS7671 or any Malaysia authority standard, and lastly, to evaluate and analyze the active power absorbed by the loads by using 2 wattmeter method and the conventional measuring method. So this experiment actually should be performed by using at the laboratory lab, but we have performed this by simulation using eSIM software. So if in the laboratory, we should use maybe the EMS workstation model 8110, a unit of resistive load 8311, a unit of power supply model 8821, a unit of data acquisition system, data acquisition interface model. So now the transmission impedance for me given as according to the matrix number. So 59 ohm plus J13 ohm was connected to each branch of the three-phase Y generator. The line-to-line rating was set to 11 kilovolt. So the frequency of the phase voltage of the generator was set to 50 Hz as stated in Malaysia standard according to the ESA version 3. So a balanced impedance load of 81 ohm plus J9 ohm according to my measuring number with Y connection was connected to the generator. So 2 ammeters and 2 voltmeters was connected to the system to resemble the 2 wattmeter method. The parameters of the electrical system in the context of transmission and load impedance, currents, voltages, and acceptable voltage drop based on BS7671 was evaluated. Not only that, the active power absorbed by the loads was analyzed by using 2 wattmeter method and the conventional measuring method. Analysis, discussions, and conclusion were made according to the data obtained from this project. So for the result and discussion, given that the impedance load uh, at the transmission loss was let's say that were XL4, XL5, XL6. Hence the was 81 ohm plus J9 ohm. So the value of the inductance L4, L5 and L6 is equals to, we know the load impedance is equals to 2 pi FL. So the inductance we can conclude as 0.02865 Henry. So for the transmission impedance, the value of the inductance could be 0.04138 Henry. So the phase voltage of the voltage supply, V supply, can be calculated by using the equation voltage line to line equals to 3 times the voltage phase, which is equals to, so the voltage phase is equals to voltage line to line divided by 3. So 11 kilowatt voltage line to line rating given to me. So when it is divided by 3, we could get the voltage phase of 6.35 kilovolt. Since the load impedance connected were in a balanced condition, where the resistance 4, 5 and 6 were equal, hence the value of the current IN is equals to 0 ampere. The phase currents of the load are 44.8 degree ampere, with the IAN has a value of negative 8.93 degree, while IBN has a value of 111.07 degree as the argument, with 44.8 ampere, and the ICN is 44.8 ampere as the magnitude, and the argument was negative 128.93 degree. Since the line current IL is equals to the phase current, so we can also conclude that the I phase at the load A, I phase at the load B, and the current phase at the load C were equal to the IAN, IBN, and ICN at the generator. So to find the acceptable voltage drop value, V load, it has to be determined first and foremost. Since the Y connected loads were under a balanced condition, where the impedance of the load resistance and the transmission loss were equal, the value of phase voltage of the loads are 3.65. We can use the formula V phase equals to I phase times the impedance at the phase. So by using the formula, we know that the impedance was same at the load, but the currents were changing. With there is a change in the argument of the current, with magnitude being the same, which is 44.8 ampere. So we can use the voltage phase, we can detect by using V equals to I Z. So the voltage at the phase A at the load 3.65 kilo volt, with the argument is negative 2.59 degree. At the phase B, it is 3.65 kilovolt with the degree 117.41 degree. And the voltage at the load C, it is 3.65 kilovolt with the negative 122.59 degree volt. So the value of acceptable voltage drop percentage, which is voltage drop percentage, can be computed by using the equation the difference between the voltage supply and the voltage load divided by the voltage supply times with 100%. So the voltage supply that I have acquired from this project is 6.35 kilovolt minus with the load voltage at the load, which is 3.65 kilo, divided by the original voltage supply, which is 6.35 kilovolt, times with 100%. So the answer would be 52%. So the line-to-line voltage at the load are calculated as the voltage at the load calculated as 3 times with the voltage phase at the load. So the voltage line to line A is equals to 6.32 kilovolt with the degree of negative 2.59 degree. So voltage line to line B is equals to 6.32 kilovolt with 117.41 degree, and the voltage load at C is 6.32K with the phase of negative 122.59 degree. So the active power absorbed by the loads can be determined by using 2 wattmeter method as we mentioned earlier. By referring the ESA version 3, for the suitable power factor value, it is stated that load power factor should be maintained to a minimum of 0.85 for voltage level less than 132 kilovolt. Since my level is less than 132 kilovolt, so we will use a power factor lagging 0.85 for the electrical system that I have been studied. So if the power factor is, we can use a 0.85. So we get to know that the angle is 31.78 as the PF is equals to cos theta. So if the power factor that has to be maintained is 0.85, so we can acquire the theta, the angle is 31.788 degree. So the active power measured by the wattmeter W1 and W2, we can use by the formula W1 which is the power measured by the wattmeter, which is equals to the product of voltage and the load times with the magnitude of the current of the load with multiplied by the different cos of difference between the T and the theta I mentioned earlier. So it is for omega. There are 2 wattmeter method, so one is minus and another is plus. So we get the formula, the answer for wattmeter is 282.988 kilowatt, and for the second wattmeter is 138.85 kilowatt. Thus, the active power absorbed by the loads can be obtained by the sum of the reading of the both wattmeter. So the total active power was 421.8485 kilowatt. Based on the conventional measuring method, the active power absorbed by the loads is equals to 3 times the voltage phase of the load and times with the current of the load times with the cos of difference of the theta. Hence, we can get the answer is 487.926 kilowatt. So that is a significant difference in the value of active power absorbed by the loads between measurement of 2 wattmeter reading and conventional measuring method. This is because of the power loss due to the transmission impedance of the reactive power. As we know, that is resistive and inductive load and the cable use. Now it is proven that the sum of 2 wattmeter method is approximately equals to the active power of the load. So as the conclusion from this project, for 3-phase systems, the current coils of 2 wattmeter are inserted in any 2 lines, and the potential coil is connected from its own current coil to the line without the current coil. The sum of the power measured by 2 wattmeter is equal to the total instantaneous power absorbed by the load. So the reference that I have used for this project is the Tenaga Nasional Berhad Electricity Supply Application Handbook version 3.1, which is ESA version 3. So that's all. Thank you.